In many applications, robots are required to collect semantic information of their surroundings, one simple form of which is object class information or object classification. Consider a robot which moves near an object of an unknown class. At time k, it acquires some sensor observations and control inputs. We are interested in inferring the object class given the history of observations or the object class posterior at time k, which we call the belief. One of the challenges is that some views of an object may be confusing, causing wrong classifier output. For example, while in the left view the dog is classified correctly, on the right the highest score is assigned to a wrong class. This can be further aggravated when using the common assumption of independence of observations, whereby class likelihoods are multiplied element-wise, leading to overconfident posterior, in our example inferring a wrong class with high confidence. Another issue is difference of runtime input from training set. For example, a classifier trained to recognize a fan from certain viewpoints, getting views with partial occlusions, unusual viewpoints, fans that look different from ones it had been trained on. While we constrain what happens near training data, for inputs far from the training set, the output is increasingly uncertain. In our work, we combine a technique to approximate such uncertainty in neural network classifiers by applying dropout at test time, yielding for each input a set of classifications characterizing the uncertainty, with special class models as proposed by TC and by Velez. The latter, however, require robot localization, which is generally not known precisely. We propose a classification fusion scheme which does not assume non-localization, uses rich classifier output, namely set of classification vectors characterizing the classifier uncertainty, and accounts for viewpoint dependence and correlations. We start by marginalizing of a robot and object pose to separate the problem into classification with non-localization and that of inference of localization, which reduces to standard SLAM. Further details are in the paper or at our stand. Presented graphs compare the probability assigned to the correct class by our scheme to a method as proposed by TC et al. In a MATLAB simulation. One step of color intensity indicates a 10% percentile step. The dark lines denote the mean. Our method, shown in blue, robustly accumulates confidence both in presence of heavy classifier uncertainty on the left and of localization error. In conclusion, we proposed a method for classification fusion aware of viewpoint dependence and robust to uncertainty in localization and classifier output, and demonstrated these properties in initial simulation. Thank you for watching, and we will be happy to see you by our stand.